But first, I'll talk a little bit about my history with data and sort of why I got into sort of data in the first place. So it's probably not a huge surprise, but I'm kind of a bit of a geek. So a long time ago when I was a kid, I used to actually joke around with my dad about how much data could you store about everyone in the United States? And yes, this is a little bit US-centric because we were in the United States. And the little sort of anecdote we came up with was, let's imagine that you wanted to store information about everyone in the US, that's about 300 million people. You wanted to do it for about $1 million, and you wanted to keep 3 copies of each piece of data because you wanted to keep it safe. So the interesting thing is what's changed over the last 30, 40 years or so. So in 1980, hard drives cost $193,000 per gigabyte, and so you can store about 6 bytes per person, which is really nothing. By 1987, you can get up to 26 bytes per person. Again, not very much. You can store a first name, email address, maybe a social security number, something like that. By 1997, right, if you look at the 1987 to 1997 change, it went from $45,000 per gigabyte to $100 a gigabyte, right? Pretty significant change. Now you're storing 11K per person. That's enough for, all the meta information about a person plus a pretty little crappy picture. Fast forward to 2007, 50 cents a gig, a 200x improvement from 1997 to 2007. Right, 2 megabytes per person's a lot. Fast forward a little bit further to 2017, we're down another order of magnitude, 4 cents a gig. I think in the last year, this has come down another 2x or so. I think we're at around 2 cents a gig right now for sort of modern hard drives, and they're faster than they were before. And the point of this is really that the assumptions that people made when people were designing sort of systems 10 years ago or 20 years ago no longer hold. Right, the assumptions were that data was sort of reasonable size, and you couldn't keep everything. Right now, you can keep every piece of data that you ever collect as a company and store it because hard drives are actually that cost effective. People assume that the systems that people were building, in the 70s, in the 60s, the sort of the traditional relational databases, were designed in the era when hard drives cost $100,000 per gigabyte. Right. Things have completely changed around everything around how computers are built, how hard drives are made, how people deploy applications, what programming languages people use. Sort of every assumption has sort of been thrown out the window. So that's sort of some pretty base assumptions that have changed. So let's talk a little bit about me. That's always a fun topic. So how did I get into the data space? So I first started working on sort of large data problems around 2000. And at 2000, I was at DoubleClick. For those who don't remember, DoubleClick was the first internet advertising company. DoubleClick had the great honor of inventing the pop-up ad. DoubleClick also was the company who first started misusing cookies. So all those little notices on websites, you can thank DoubleClick for that. So in 2000, we were serving 20 billion ads a day. We were doing that across 10 data centers around the planet, around 500-ish servers, and one really big Oracle database sitting in New York City. Yes, it was actually sitting in the middle of New York City for reasons that are a little bit strange. And so there was a number of challenges with that. So one of the challenges is that we need to serve ads everywhere on the planet in less than 60 milliseconds. So obviously, if you're trying to serve an ad in Tokyo, there's no way you can go back to New York and get any data in 60 milliseconds, right? You've got to keep data sitting in Tokyo. Okay, so now how do you do that? Right? The networks weren't that fast. You can't actually do computation across the planet that quickly, so what did we do? Well, we dumped a 40 gigabyte CSV file every night and sent it to every data center around the planet. It's a nice little hacky solution, right? We were trying to hack around the database because we needed to figure something out. During the day, we were trying to serve the right number of ads. So what did we do? We wrote a little UDP system that kept little counters and sent counters everywhere around and tried to do sort of basic synchronization of data. And then every night, we would go ahead and send all the actual correct data back to New York and create a clean copy of that data. Right? Of course, what that means is during the day when you were actually serving ads, no one had any idea what was actually happening. Right? You just heard this vague notion that ads were being served around the planet, but you couldn't actually really tell what was going on. You couldn't really know what was going on, and if you wanted to change what happened on an ad serving in the middle of the day, completely impossible. The other kind of interesting thing about this system is that every Saturday, we had to take the entire ad trafficking system down for database maintenance. Right, so this was 1999. This is sort of what was going on. Everything, so if you wanted to sort of change the ads that were being served on Saturday, you just couldn't do it. We took the whole system down. It's kind of like a little break for the database. It's fine. So that was my first foray into sort of large data systems. So after DoubleClick, I started a company called ShopWiki. ShopWiki was an e-commerce site, and the interesting thing about ShopWiki was that we were crawling the internet looking for things you could buy. So at ShopWiki in 2005, we were crawling about 350,000 stores on the internet. We ended up creating a database of 500 million products. And it turns out products on the internet changed really fast, even in 2005. So how did the system work? It was pretty straightforward. We had a bunch of websites that we were crawling. We had a whole fleet of web crawlers that were crawling the internet. And we had a sharded MySQL system. We had 11 shards. At some point, we wanted to change the 11 shards to more numbers of shards, but it was impossible because we built our whole manual sharding system that put data in the right place and sort of made that happen. And sort of changing that structure was basically considered way too hard, so we just kept getting bigger boxes. So it was great that it was sharded, but we couldn't actually do anything with it. And then for every copy of the data, we also had to have a separate index for doing searching, because you couldn't actually do searching out of the database. That was not possible. So this was a pretty complex, hacky system that we built, but it worked effectively, and it lasted quite a while. The other challenge that we had, so we had this sort of manual sharding challenge. We also had the synchronization challenge. What we had to do is we had to synchronize all the data from the root MySQL system to both the search system, to a separate analytics system, and to a bunch of other sort of third-party vendors that we were sort of sharing data with. And all of that synchronization was sort of hard to build, right? All the sort of custom logic. So besides sort of scaling and synchronization, we also had sort of root data modeling problems. So it turns out when you're looking at products across every catalog, every type of product on the internet, there's about 30 or 40,000 different types of attributes a product can have. So things like brand and color and size, right? So 30 to 40,000 different types of attributes. Any individual product only has around 30. So now if you try to model this into a relational database, you can imagine what you're going to have. You're going to have a product table with like a title and an image, and then you're going to have a product attributes table with a product ID, an attribute ID, and a value. So this kind of works. You can sort of imagine what it would look like. But when you're actually trying to work with it as a developer or sort of search it, it became incredibly inefficient and incredibly slow. You need to work around that. And also, we really wanted things to be more real time. So imagine, Cyber Monday started to be a thing, and we wanted to have the actual search index updated in almost real time as we crawled the internet. It was also impossible, right? There's no way this system could work in real time because everything had to be batched to make it actually scale. So all the challenges we had at ShopWiki really was sort of the beginning of sort of the modern application era, right? When user expectations of websites and applications were starting to change pretty dramatically. And so I think ShopWiki is a good example of a very early modern application and the sorts of challenges modern applications have with data. So if you think about sort of how the ShopWiki challenges correspond to sort of modern data requirements, right? Manual sharding turns into there's a lot of data out there, and you need to make it scale. Manual synchronization is there's lots of use cases for data, right? Every person I talk to, they have a set of data, and they want to reuse that data for many different applications, many different use cases, many different users, for analytics, for different transactional systems, lots of different copies. The schemas people's data schemas are changing very rapidly as well, right? As you add new features, as the data models change, you just want to add more and more features, more and more attributes, collect more different kinds of data from different sources and merge it together and make all that happen, again, in real time. And you want it all to happen in real time, right? There are no delays. The other thing that you want is you want this all to work easily for developers, right? You want it all to happen pretty nicely. And so modern applications really are equatable to modern data, right? Almost every modern application is working with sort of data, and almost all modern applications want to use data in sort of this very modern way. So what exactly is a modern application? So what characterizes a modern application? Is everyone here building one? So I think there's sort of three characterizations of what modern applications really mean. So one is developer agility, right? It is more important now than ever that developers can actually get their job done quickly. What does that mean? Adding new features, getting new products to market. Sort of developers are, I think a lot of people here are probably developers. Developers are more expensive than ever before. And every company I talk to is always wants to be able to hire more developers and make all the developers that they have work more efficiently and work faster. Right? That's more important than ever. Infrastructure agility, being able to deploy things in different ways, and sort of an uncompromising user experience. So if we dig in a little bit, so in developer agility, it really comes down to high productivity, right? You want your engineers to be able to write code quickly, to actually spend their time writing code rather than having to sort of work around problems, and you want them to focus on the right problems. And you want them to be able to release features quickly. Right? I have never met a company who said, yeah, my developers are going too fast and my features are coming out the door too fast and I can't come up with new ideas. Never happened. Right? There's always a massive backlog of features and products that people want to build, and the development is always the thing that's sort of slowing people down. So infrastructure agility to me really comes down to a few things. One, it's automated. Right? You want your infrastructure to be fully automated because no one wants to be doing manual things. No one wants to sort of go and have this whole notion in DevOps of sort of generic machines as opposed to sort of very specialized machines. No one really wants that. Right? It's the sheep versus pets notion, something like that. I can't remember the exact words. You want it to be platform agnostic. Right, wherever you want to run your application, you don't want to have to sort of say, well, I can't run this application here because it doesn't support this thing. I don't really care about that. You want it to be fully elastic, right? So as you scale it up, you can just sort of add more capacity. As you scale down, if you need to, you can scale down, but sort of a fully elastic system. And you want it to be deployable no matter where you are, right? Whether it's on a private cloud or on a public cloud or any public cloud that you want, right? You want it to be agnostic, so you can just deploy this wherever you want. You don't have to sort of you don't want to tie yourself to one decision just because you use some product. And then you also want an uncompromising user experience. So real time, right? No one wants a delay, and no one wants a delay really on anything. If I go and use a banking app and I sort of I'm supposed to be getting a deposit, I want that to show up in my app instantaneously. If it takes a few hours to show up, I assume someone's trying to rip me off or something. I want it to be global, right? I want my data to live everywhere on the planet. Because if I get on a plane and go somewhere, I want my application to be fast. If I have users who happen to be in a different country or in Australia, I want my application to be fast there. I don't want it to be a shitty experience just because I live on a different continent. I want it to sort of be able to plug into anything else that I want, to third-party applications, and sort of be a hub and not just sort of a bespoke data set that I can't actually put anywhere else. So when building a modern application and you're working with these data, we're having these requirements, there's a number of sort of challenges that people have. I'm sure most of you here have had one of these challenges before, if not all of them. So the first is the size and cost of data. So now that hard drives are actually pretty cheap, the whole notion about data has changed. You want to be able to store not like a little bit of data about what you're doing, or not like some data, but you really want to be able to store everything. Right, the whole notion today is let me store every event, every log entry, absolutely all the data that I can possibly imagine, because hard drives are relatively cheap. And of course, that data might be useful at some point in the future, so why would I get rid of it? Of course, now you have this notion and sort of product managers saying, I want more data, I want all the data, like don't never delete anything. You still have to manage it, you still have to store it somewhere, you still have to sort of have a catalog of what it actually looks like, you still have to be able to actually get to the data. And that adds just cost and complexity to systems. You want all the data to be accessible and sort of fast. So I'm sure a lot of people remember when sort of banking apps or credit card apps started first becoming available on the web, and you can sort of see a bank statement online. You saw like, hey, you can get like today's, this month's bank balance, and maybe you can see a statement from last month and maybe 2 months ago. And if you wanted something from more than 6 months ago, you had to send them an email saying, hey, can you go get me this statement, right? It wasn't just available online. They were probably getting it from some tape backup or scanning it from somewhere. Today, that's sort of completely unheard of, right? Imagine if like Gmail said, oh, if you want an email from more than 6 months ago, that'll take you a month for me to retrieve. Right? The whole notion is that all data should be available now, pretty quickly, right? If I would go and look at an email from 2 years ago, I shouldn't have to have a really shitty experience just because I'm looking at an old email. And the data has to be where it wants to be. So it has to be where your users are, right? So if your users are in different places, it has to be accessible quickly for them. It has to be where different kinds of users want to get access to it from a use case standpoint. So if you're doing analytics on that data, I have to be able to put it in sort of different systems so I can get access for business analysts or someone else to go look at that data. Or maybe I'm working in some sort of a regulated environment where data has to live in a certain country, where I've got PII from a German citizen that has to live in Germany, or Japan and Australia are writing these rules, or it has to live in Europe because no one trusts the United States with any data. So things of that nature, right? Data has to live in certain places, but at the same time, you want one logical view. So as an actual developer or sort of a sysadmin, you're not looking at 50 different systems to actually get a holistic view of your data. You still want one sort of view of everything. And of course, the more data you have, the more of a target you become. So everything has to be stored incredibly securely, incredibly safely, because otherwise you're just going to be in the news, and that's no fun for anyone. So how can you go ahead and build a data platform? How can you sort of build an application that actually solves all these challenges? And so I think there are really sort of three concepts that if you can sort of stick to when designing a modern sort of data application, no matter what product you use, things are going to work pretty well. So those really, for me, come down to three things. One, a rich structure for how you can store the data. Two is an intrinsically distributed system. And three is a system that you can run anywhere. So let's take a look at a rich structure first. So for a rich structure, I mean something more than just tables and rows, right? More than just Excel on steroids, which is kind of what a relational database is. So maybe it's a JSON, storing JSON documents or some sort of hierarchical thing. I guess XML technically counts, but I don't think anyone really wants to use XML. But some sort of structured document. So why would you want to do this? Well, first, it's easier for developers. And why is it easier for developers? Because documents map naturally to the way that people think. When people think of a person, they don't think of them as sort of this deconstructed thing where they put different attributes in different places. They think of a person as sort of a single entity. And they think of that single entity as something that they can interact with. And when you think about programming languages have gone this way as well, right? Object-oriented programming, sort of document-centric programming, right? Every program anyone writes is going to have some sort of structure that represents a person or represents a car that you can interact with. We don't break things apart, we put them together. And a sort of a rich structure, you can store things in that natural way. In addition, it maps very cleanly to the way you write code, and so it's very easy to just go ahead and store data. Now, of course, a lot of applications are built on either microservices or have some sort of APIs, and most of those services speak some sort of JSON over HTTP, right? Sort of the standard REST API for storing for data. So if you've got some sort of rich structure in your database, now your REST API becomes sort of exposing that data to the right people at the right times, not about trying to find a reconstruction of that data in some weird way, right? Just letting you serve up the data in sort of its natural form. And it also lets you have just less denormalization, fewer copies, where because every system that I've ever seen where there's sort of a REST API that sort of goes and queries a relational database, what does every one of these systems have? They've got some sort of caching system, right? They've got some sort of system that takes this relational database, takes the joins that people are doing, and caches them somewhere because that's the only way to make it scale. So those are things you really don't want. You don't want to have to do that, and you want to be able to just store it in its natural form. So what are you not willing to give up? So modern sort of rich structured databases that even support documents can support things like very efficient queries, very efficient writes, right? You shouldn't sacrifice performance just to get this. You shouldn't sacrifice having to sort of have a schema, right? I think schemas are one of those things where they're good in some cases, less good in other cases, and you want the flexibility on a sort of per application, per collection basis to say how much schema is the right amount, how much do I want to have flexibility, and how do I want it to change and evolve over time. You also don't want to have to give up ACID transactions, because again, in a document sort of model or in a rich structure model, in a lot of cases you don't need transactions, but sometimes you do. So while you don't want to necessarily give those up. And you want something that lets you, be anywhere, right? And sort of use a format that is used anywhere, something like JSON. But if you use JSON, you can sort of say, well, this is I can use it in my database, I can use it in my REST APIs, I can use it in my web application, I can use it on a phone, I can use it anywhere. So you want something that sort of uses something pretty ubiquitous, and you want a great query language. Right? You don't want to have, just because you're storing a rich structure and you get all these things, you don't want to have to give up a sort of a nice query language and have to write like a MapReduce query just to look at the data, or have to put the data in a different system analytics that sit on sort of one system. So what are some things you really want to avoid? Well, you don't want a schema nightmare. So at DoubleClick, we used to have these very painful weekly schema change management meetings. We want to get rid of those. You don't want to take your database down for maintenance on the weekends, because that's kind of painful. So that's rich structures. So next is distributed intrinsically. So what are some things why might you want to do that? One, so distributed systems are inherently going to be more scalable, right? So I would say, you know, 1 million writes per second is kind of nice, but I see systems all the time that are much bigger and much faster than that, so massive scale. You want to be able to do things like workload isolation. Distributed systems lets you put different data in different places for different kinds of workloads without having to sort of do your own synchronization. Distributed systems are sort of highly available by nature as well, so you don't have to worry about sort of machine crashing, things going down. And they let you do things like use different kinds of storage engines. So you can have some data that sits on sort of SSDs, some on spinning disks, and some on S3, but use sort of the same query language to get at the data, the same way to sort of make that system work. What are you not willing to give up? You're not willing to give up things like triggers or real-time events or streaming. You shouldn't be willing to give up consistency, right? Because consistency is actually quite useful. And again, you shouldn't be willing to give up transactions just to get distributed systems, because, you know, why would you? So things you want to avoid: manual sharding, because manual sharding is painful and hard, and it's going to break. And you also don't want to build your own synchronization layer, because something's probably going to go wrong unless you're a real expert. So third is, of course, you want to be able to run this anywhere, right? You want to be able to run your database anywhere. So what do you want to do? You want to be able to have the same architecture from a mainframe to containers. Right? It doesn't matter if you're running on an IBM Z series or in Kubernetes. You want it to work. You want to be able to migrate from a private cloud environment to a public cloud environment, or really any, and not just one public cloud, but any public cloud, so you're not sort of beholden to any one company. I think it's a lesson we've learned in the past. And you might want to be able to keep the data sitting on a phone as well, and synchronize the data from your private cloud to your phone or the public cloud to your phone, so if someone's working offline, things actually work. And what are you not willing to give up for this? Well, you don't want vendor lock-in. I think it's a lesson we've learned over the last 30 years, is being locked into any one vendor, or when they have too much control over you, bad things can happen. And you're not willing to give up powerful features, right? You don't want to sort of have to code to the lowest common denominator of database features, because then you're going to end up spending a ton of time working around your data rather than actually letting the database actually do what you want. So you don't want to go and hire bespoke programmers with very few very specialized skills, because that's just going to be impossible to hire. And you don't want your developers who are on airplanes to have to go and watch Paddington 2 instead of getting code done, because you can't actually run your application on your laptop. So let's take a quick look at sort of what kinds of databases and what kinds of database platforms actually support these kinds of things. So first, with rich structures, there's a bunch of databases that sort of support JSON documents. Obviously, MongoDB has always been a document database. That's sort of why I'm here. MySQL and Postgres have sort of added JSON support over the last few years. The challenge there is it's sort of not terribly native, and it's sort of hacked into SQL, but they technically let you do it at least. And DynamoDB lets you store documents, but you can't actually query them. So that's sort of useful, but sort of not useful. In terms of intrinsically distributed, Aurora's got some, Aurora from Amazon's pretty distributed, but again, you're locked in and you can't do things, other sorts of things. Things like Cassandra are sort of intrinsically distributed, but only give you some benefits. And MongoDB is distributed and has lots of great benefits as well. And you want something that really runs anywhere. You want something that is sort of open source, that you can actually go and use yourself if you want. Something that you can run on a phone, on a mainframe, or in any public cloud. That's what you're really left with. And so I'd be kind of amiss if I sort of came here and didn't at least make one little pitch, which is that there's one thing that does fit into all three of those buckets pretty nicely, and that is, of course, MongoDB. So you should take a look if you haven't already. And sort of why is big data and modern data so important to applications, and why is building a modern application so important? And it's like, do I need a modern application? Can I have a non-modern application? And I think the reality is everyone's business is an app, right? Whether you're a bank or a telco or an insurance company or a startup, right? Your app is the way that all of your users actually interact with your system. And if your users have a great experience with your app, they're more likely to like your company, like your brand, and sort of be engaged. And if there's a bad app experience, every experience that I've had and people I talk to, if they don't like your app, your company's going to have more trouble with that as well. And whether you use MongoDB or not, I really believe that any modern data solution that really supports these rich structures, is intrinsically distributed, and runs everywhere, is going to work pretty well for you. But I think these three principles are sort of the most important aspects of this. Thanks, and I think I may have like 2 minutes for Q&A, is what they told me. So if you've got any questions, now's the perfect time. And if not, we can just end right here. Great, so it's great talking to you this morning. Thanks for coming, and hopefully I'll see everyone soon. And